Well, we're going to talk a little bit about a different type of quantum computer, quite different in fact, and it's the D-Wave, and it's a quantum annealer. So we're not going to talk too much about gates. In fact, we won't talk about them at all. And we won't talk too much about physics, but if you're interested in sort of what real people have done on a real quantum computer, we're going to show a lot of examples of what our customers have done. So with that, we'll just sort of launch a little bit of background, some things we've done to make it easier to access our machines, and then most importantly, we'll spend about 2/3 of the time talking about what real people have done, and then wrap up. So I first met Richard Feynman in 1983. I ran computing at Los Alamos then, and I was youngish then, I guess. And it was the 40th anniversary of Los Alamos. This was the program from the time, and Feynman gave a keynote address at first thing that morning, and it was entitled "Tiny Computers Obeying Quantum Mechanical Laws." First time I'd ever heard of quantum computers, and a couple of days later, Feynman and half a dozen other Nobel laureates wanted to see what modern computing was like at Los Alamos, and so I was taking them all on a tour and standing in front of one of the crays, and we had the most powerful scientific computing facility in the world at the time, and I'm standing in front of this cray saying, and this cray behind me can do 160 million calculations a second, and we have 5 of them. And plus all these other controlled data equipment we have and stuff, we can do about 1 billion calculations a second. Of course, your cell phone can do that today, but it was, quite an impressive thing. And Feynman said, I doubt he even remembered my name, because he said, young man, someday all of these big crays are going to be replaced by a quantum computer. And I said something very unremarkable like, wow, or cool, or something. We weren't up to awesome, or those more modern words. And that'll come back in a second. It's taken 35 years, but 35 years later, Los Alamos became our 3rd system customer, so we in fact have a system installed there. The idea behind, so people started immediately working on quantum computing, mostly around gates, building gates and gate model sorts of things. But about 20 years ago at Tokyo Institute of Technology, Professor Nishimori and his student Katawaki-san wrote a paper for Katawaki-san's PhD thesis, and it was quantum annealing in the transverse Ising model. Interesting paper, they wrote it, and didn't get too much notice. And in fact, I was in Japan last week, and Nishimori-san was given a big award, a Lifetime Achievement Award, and we spoke at it and those sorts of things. And he recounted that after they wrote this paper, the first review of it was, "It'll never fly." Basically, this is sort of interesting science, but nobody will ever do it. They didn't patent the idea or anything. And then our friend Eddie Farhi and gang, Eddie might even be here today, wrote another paper a couple of years later about adiabatic evolution, and and others from the academic community wrote other papers and did experiments and things, and that kind of led eventually to the folks who had found a D-Wave to be able to start building this computer. And this is the circuit diagram of the D-Wave computer. It's you can think of it as kind of a quantum analog computer. And this is kind of a way to think about how it works. So imagine that you had a problem that you could map onto a mountainous landscape. This happens to be the Beartooth Mountains near where I live. And what this computer does is, without adding or subtracting, it finds the lowest valley or valleys in that landscape, probably. Ours is probabilistic, not guaranteed that you found the lowest valley. So people don't run a problem once, they'll run it 100 times or 1,000 times or something and get a distribution of answers. And if the problem is like the Beartooth Mountains here, which are a little exaggerated in the z-scale, but if it's like the Beartooth Mountains where there's steep, rugged mountains and some clear, low valleys, if you run a problem 100 times, you might get 91 answers in the lower right down there at Green Lake, and you might not get any answers up there in the bigger lake, Glacier Lake, up higher. And so it'll be a distribution of answers, but most of them, if it's a rugged landscape, will be in the lowest valley. And then you'll get a collection of them elsewhere. But if your problem is more like the Sahara Desert, you'll get answers all distributed all over the place. And what's really happening is the machine is really sinking to a low energy state, or collapsing, we say, to a low energy state. So it's not really a three-dimensional landscape like this, but it's an n-dimensional energy landscape, and the machine sinks to a low energy solution, and we're able to do that about 5 to 10,000 times a second. So it's more like an analog computer of the old times with some quantum aspects thrown into it. And the challenge with it is, it's conceptually sort of simple, but the challenge is, how do you map real-world problems onto it? And so 2.5 years ago, if we had had this meeting, I would have told you about map coloring. That was the thing that really we had done, and to be able to demonstrate how to use the machine, that was sort of the application that we use. In fact, Mike, I think that's you in the front, would remember map coloring. And then a couple of years ago, we would have shown you maybe 25 applications, mostly from Los Alamos and our friends at NASA, and a little bit from USC. And now we have about 100. So the progress in thinking about how to map stuff onto these energy landscapes has been dramatic. And we'll show you what that looks like. So D-Wave as a company was founded about 20 years ago as well. And we provide computers and access over the cloud and work on apps projects with people and training and all of those sorts of things. We have systems installed at Lockheed Martin and USC down in Southern California. It's ISI, the ISI part of USC. We have a system about a half a mile that way, I would say, at Google and NASA. Its systems actually installed at NASA Ames. USRA is our actual customer, contractual customer, and does a lot of work on the system. Los Alamos became our third customer. And then Oak Ridge uses about 20% of a machine, aiming toward our machine being an accelerator for exascale as it comes along. And the idea of it being a low-power accelerator is kind of what they're aimed at as well. And then at those sites, there are another 50 or so collaborating organizations who use our machines, another 35 or so cloud customers, mostly industrial customers. And then they've ended up developing about 100 of what I call early applications or prototype applications, proto-apps sometimes. So that's kind of a snapshot of D-Wave, how to think about it. We actually have a chip. This one has 2,048 potential qubits in it. We usually lose a few as well. We call it the D-Wave 2000. So the idea, that you don't want to call it the 2048 and then lose a few qubits. So we call it the 2000. But they're running in the 2020 or 30 or so qubit ranges. And this chip is installed here. There's one installed here at Google. And Los Alamos, we've just finished one there as well. And then we have some in-house. And our hope is that the Lockheed machine would be upgraded too. And then we'll have a few other customers. We've been able to roughly double the number of qubits every couple of years. The first machine went to Lockheed, had 128 qubits, was since upgraded to 500 qubits, and that was about 6 years ago. Since upgraded to 500 qubits and then 1,000 qubits. Google and NASA Ames and USRA started here with 500 qubits about 4 years ago, upgraded it to 1,000 and then 2,000 qubits about 1 year ago. And then Los Alamos 1,000 and to 2,000 qubits. I would just say the next machine on our horizon is probably a year and a half away, and we're expecting it to have 5,000 plus qubits in it. I would also say for the gate model folks, our qubits are not of the same quality as yours are. They don't have to be. It would help if they were, but they don't have to be. In a sense, our architecture is more forgiving of quality of qubits and those sorts of things. It's a little more fault tolerant, if you will, or error tolerant. So we're on a quest to increase the number of qubits, really increase the connectivity between qubits, and then can improve the quality of the qubits to reduce the noise and intrinsic control error and be able to let us get to bigger, better answers more quickly as well. So all of those things are sort of in the n-dimensional space that we're attacking as we develop new products. So this was Mr. Feynman's famous book, Surely You're Not Joking, Mr. Feynman. You'll remember earlier I said that Feynman said to me, young man, someday all of these big supercomputers are going to be replaced by quantum computers. He wasn't quite right. because like everyone else has talked, our machines go in side by side with existing computers. And that hybrid model that we've all talked about is the same one that we see. And again, we'll show you examples of that. So we've just introduced in the last couple of months a new, much easier way to get onto the D-Wave machines. We call it Leap, D-Wave Leap. The folks at our desk out front will talk to you about it. You can get some free time if you want. There's some conditions for putting your developments in the open source to continue to get free time, but it's easy to get on, easy to use, and I would encourage you to look at it. And then we have new improving software tools all the way from sort of the bottom up higher, and those are in Ocean, and again, you can get more information about those. And then just yesterday, we announced what we call D-Wave Hybrid, and it's the same idea that we've heard about from others, and that is to enable much more easily to develop applications that are spread between traditional computers and ours. So it's available starting now for developers in sort of an early release version, and folks can try it out, and then we'll improve it as we go along. So with that, I'm going to switch now and talk a little bit about applications. And of course, these are we have a new category here that you haven't seen from other folks, fiction. We'll do that at the very end, and a little quantum fiction application. But in terms of all of the applications that customers have developed, and again, this isn't us now, these are customers, there are about 100 of those early applications. And of those, about half are oriented toward optimization, about 20% machine learning of one kind or another, about 10% in growing material science, and about 20% are a whole collection of other things. And we'll show you what a lot of those look like. Also, at the very end of the presentation, I have some websites where the customers have made presentations, and all of those are available to everyone. So Chad, you don't have to take notes about this. You can, I'm teasing, of course, my friend Chad, but folks, Julie, you can take notes, though. So, this is open. We're in the days here of a rising tide lifts all boats, and I think we're all advantaged by all of us doing better as we move along. The one thing I would note is that on these, maybe half of them are approaching classical results or a little better quality of answer, but always for small problems. We can't solve real-world production problems yet, always small problems. But I'll show you at the end that there are 3 or 4 that are getting closer, I think, to pointing toward real-world, smallish still production problems, maybe in the next year or so. So we'll show you what those look like. Okay? The installed systems, the big customers, these are the major application areas that they're working on. Lockheed started with software verification and validation. Google and NASA Ames started with machine learning, but the NASA Ames side in particular and USRA have looked at a whole host of other things. Los Alamos has probably looked at the broadest set of different applications. They have a whole website now with 30 plus of their early applications on it that you can look at. And then Oak Ridge is similar to Los Alamos, but with a little more emphasis on material science and chemistry. And then for folks who are accessing the machines via the cloud, I've just selected a few of them, and we're going to really walk through these, but they include VW working on traffic flow optimization, internet advertising from Recruit Communications in Japan, tsunami evacuation, and on and on. So maybe rather than just saying this, let's look at what some of those look like. But first, I would say at the existing system sites, in addition to the cloud customers that we have, there are a lot of partners who are running on our installed systems. So this is from USRA, NASA, and Google. These are, and I think Eleanor might show a slide similar to this tomorrow. I think she's on. This is, in fact, one of the slides from here. And you would see a whole collection of names that you know who are collaborating on projects here with USRA and NASA and Google. And then the same thing for Oak Ridge. These, again, and almost all the slides from here on out are customer slides. So you see a lot of great names of folks doing things on our machine. And then the first quantum application that you could kind of explain to your parents was, I think, what Volkswagen did. And this is now nearly 2 years ago. The VW CIO called me up one day and said, I'm going to be in Silicon Valley, and I hear about quantum computing and would love to, hear what you all are doing. So we met with him, and he said, cool, I would like to try a real-world project. And they had some candidate projects to look at, and we helped sort of figure out what we might be able to attack. And they said, let's do traffic flow optimization. It's a real-world problem, affects everyone. And we have the data of the locations of 10,000 taxis in Beijing every 5 seconds. And so let's optimize all of the taxis in Beijing. We said, great problem, but way too big for what we can do today. But if we broke it down, maybe we could attack a subset of that problem. So what about going from downtown, the picture on the left, from downtown Beijing at the lower left of the corner to the upper right, which is where the airport is. In fact, if you look closely, you can probably see the runways and things. 400 to 500 taxis typically in transit. Still too big for what we could do on the chip. We could sort of put the equivalent of 20 to 25 taxis on the chip at one time. But by then, our software decomposition techniques had advanced enough that we could break the problem up into chunks, solve it in chunks, and then kind of glue it back together, something I think we'll all face no matter where we are in the quantum space. And then the real work started. It took about 3 months to figure out how to take this application, time-dependent, geo-located coordinates, map it onto the coordinate map of Beijing, and how do you turn that into this mountains and valleys thing? But we, working with Volkswagen, were able to do that, and the results of what they were able to do show up on the right. And the idea was, can you just sort of distribute the traffic to minimize the overall transit time? Not any one particular vehicle, but the aggregate of all of the vehicles. And, once you spend 3 months figuring out how to do it, then in fact, in 1 or 2 seconds, you'll get 5,000 pretty good solutions to the problem. You probably have the best solution, you just don't know that. But you have very good solutions, and you pick one of those and then implement that. And I think this gave Volkswagen hope, because what they said was, if we're driving, I don't want to wait 32 minutes or something before I start, which might be the time it took on a Volkswagen internal server to get to the best answer. Every couple of seconds, drivers need to know, should I go left, go straight, go right? Go left, go straight, go right. Go left, go straight, go right, or some derivative of that. So having a pretty good solution for a lot of vehicles is kind of what you need, and it looks like, as the hardware evolves, that you might be able to do that on our machines. So that gave them hope. They also got a lot of press related to that. We got a little bit ourselves, and but it was the first sort of thing you could explain to somebody in the supermarket or your parents that a quantum computer might be able to do. And then our friends at Booz Allen Hamilton do a lot of work for U.S. government projects, and they said, taxis in Beijing, well, that's interesting, but what about a constellation of satellites that have priority targets to take pictures of, and you also want to, at the same time, minimize the slewing or the rotations of the satellite to conserve energy. How about that? Let's tackle that. So these are all going to be customer slides now. These were their conclusions, and you'll see sort of a theme here that it looks like you can use the D-Wave in a hybrid environment, and it sort of was promising, and it wasn't too hard to do. So it looks like there's potential for the future. Then our friends at DLR, who were sort of the German equivalent of NASA, said, well, taxis in Beijing, interesting constellation of satellites, but what about a real problem like optimizing air traffic routes over the North Atlantic? We said, well, let's work on that, and guess what? You can at least get started on it. Their next project, and I think wherever Thierry is, there's a similar project to look at optimizing the use of gates in a concourse at an airport. So this one kind of worked. And then the next one was from friends in Japan at Recruit Communication, who said, taxis, satellites, air traffic routes, interesting, but how about a real problem like optimizing the placement of ads, internet ads on a cell phone? How about that? That's a real problem. We said, that is a problem. We can't do the real, that's very close to real-time work. We can't operate in a real-time manner like you're expecting, latencies, hybrid computing, all of those reasons. But we could probably do a test. And they said, yeah, let's do a test. And so they did, and the idea was to optimize the click-through rate, and at the same time, you wanted to maximize the click-through rates and optimize the use of the advertiser's budget through the day. And sort of the same thing. That turned out, it took a little while to figure out how to do this, but the D-Wave worked pretty well, and quantum annealing finds a better solution than the great name of the greedy method, which actually is what they use in production today. So that gave them hope. And then our friends also in Japan at the Tohoku University said, that stuff's all interesting, but 8 years ago, 20,000 people were killed in Sendai, Japan, when the tsunami came. And if you can do taxis and all that stuff, maybe we can try to help save people the next time that there is one of these tsunamis. So we're working with them on a project to see how you can use our machine to try to help optimize getting people away from the waterfront in Sendai. Huge problem, too big for us today, but they have made some progress in getting rolling. From the UK, British Telecom said, this looks kind of interesting, this optimization deal on this machine. We have a lot of problems in the cell phone networks that are really optimization problems. Plus, we're starting to have, we're concerned about malware and people improperly using our networks. So these are the 6 projects that they've started looking at. And again, conclusions from them, I'm sort of cherry-picked the slides here so we could look at many applications, but this is the conclusions that, D-Wave gets reasonable answers, and it can do it pretty quickly, and a lot of problems. And by the way, D-Wave make your machine, and it's a hybrid environment, and D-Wave make your machines bigger, better, and more powerful with better connectivity. Ocado is the world's largest online grocer that you've never heard of, and they're headquartered in the UK. And they've been working on projects to basically see if you could use our machine to help optimize the flow of robots in these factories that they have. And sort of like the traffic flow the taxis in Beijing. And it turns out that it's possible to use the D-Wave for that, hybrid computing, and pretty easy with our emerging software tools to be able to do. They're now working on their 2nd and 3rd projects about actually delivering the groceries. Switching to machine learning a little bit, a fellow here who a year ago was at SRI, a medical doctor, Dave Sonner, said, in today's world, we have more information about you, your genomics, your parents' health history, but that almost makes it more complicated for we as physicians to try to diagnose what you have and come up with a recommendation. So what if we, for each person, we were able to create a little map of you, a network about you, and we know some things shown in red here, and there are some things we don't know shown in yellow here. Maybe we could create a sort of a network graph of you and learn from a cohort of other subjects, maybe similar things, and try to fill in some of the blanks. David's gotten so excited about this, he quit his real job and has started a startup company aimed at trying to do this on our machines. And Max Henderson is here somewhere. Max did one of the wildest things ever that I wouldn't have expected. And he said, in the last US presidential election, the results were unexpected, that Mr. Trump won. And all of the professional polls were predicting that he didn't really have much of a chance. So what happened? So Max said, I'm going to see if I can map the same data, the same 538 polling data that the professional polls used onto the D-Wave machine and run it and see what happened. And the result of that was that it pointed toward, in fact, Donald Trump having a much better chance of winning than the professional polls did. And kind of what happened here, and this is sort of, machine learning meets quantum material simulation. When Max created his model, the correlation of the nodes and qubits and things on the machines is real. And Max and the model and the D-Wave noticed that there were little hidden correlations in the data, little changes in states that might cause another state to change, and those sorts of things. And that was part of what added up to this. So, and then of course closer to our scientific home, helping look through existing data, Higgs boson. Material science, Volkswagen people said, okay, we've done that stuff. Let's see if we can't start using the D-Wave for electronic structure calculations for batteries, and they were able to point to the idea that, yes, you could use it. Startup company called OTI Lumionics, working on seeing if they can design new OLEDs, organic LEDs, for use in cell phones and cell phones, televisions, and those sorts of things. And they've been able to model some pretty complicated molecules on our machines and, pointing toward the way over probably in the next generation of our product when they're getting to molecules that are sort of industrial strength. So progress there. We've also had a couple of papers that were published, one in Science and one in Nature in the last 2 months about material simulation and really trying to model the phases of quantum materials. So you can look those up. And on the cybersecurity front, this from Los Alamos, and again, it's sort of a network idea, but the idea is that if the friend of my friend is my friend, and extend that out further, is the enemy of my enemy also my friend? And so that's, in a nutshell, that's kind of what this graph process is trying to show. And so trying to figure out who, in fact, out there, unknown land, are your friends and who are your enemies. So that's all available. And getting closer to production, just in the last 2 months, I've seen now 4 things that might be pointed there. One of them is this is probably the 5th project that our friends at Recruit Communication have done. And they run the largest hotel recommendation service in Japan. It's called Jalan. And what they did was, and basically you say, okay, I want a hotel 3 blocks from Tokyo Central Station. I want it on the Marunouchi side of Tokyo Station, and I want it within 3 blocks of a Greek restaurant or something like that. And so their recommendation service gives you a list of places that you might try. And they created a model on the D-Wave to try to provide better recommendations, again, to improve the click-through rates is basically what it boils down to. They ran them side by side for 6 weeks, and they got a little better business results, meaning more revenue from the D-Wave model than they did from the traditional model. And a little bit times a lot of dollars, or a lot of yen in this case, adds up to something significant. So again, but it's a bounded problem. Within 3 blocks of Tokyo Central Station, on the Marunouchi side, there aren't millions of hotels, there are maybe 100 or something like that. So it's a bounded problem that might fit on today's technology. Then our friends from Volkswagen again, this is Martin Hoffman, the CIO, who gave a joint talk with me about 3 weeks ago in Lisbon at Tech Summit. It's one of these huge bazillion people conferences. And I did a little introduction to quantum computing, and he talked about Volkswagen applications. And I'll skip through some of this early stuff, but what he said was, we have coming future mobility systems. We, Volkswagen, are investing in those. And he said, next year, when you show up at Web Summit in Lisbon, we will work with D-Wave and with a machine learning company we have, and we'll get maps from Google and work with our partners Google, and we will have a quantum application that you can download on your cell phone, and if you want to go from here in Lisbon to there, we will take all of that into account and give you the best quantum optimized route to get from here to there. And I said, whoa. I didn't say that on stage, but I said that to him before. That's a tall order. That one's going to be more challenging to work on. But it's that sort of thing that people are seeing the possibility now being able to do. And our friends at Denso, within a factory, they have autonomously guided vehicles. And if you go to one of those websites, either in Japanese or English, you'll see how they used our machine to optimize the flow of these AGVs, as they're called. And they were able to improve the efficiency by about 15% on our quantum computer compared to what they use traditionally. That means either you can get rid of 15% of these AGVs, or maybe you can run the factory sooner. And at the end of that video, Denso says we'll be taking this technique to all of our plants. So again, getting close to smallish but production-oriented problems. In the category of fiction, who knows what this is? oh, where are my HPC friends? This is the Barcelona Supercomputer Center. And why would I show a picture of that? Because in the category of fiction, it was the place where the D-Wave wasn't fast enough, but Dan Brown wrote in an E-Wave computer to help in the book. And then secondly, in the Quantum Spy, David Ignatius, the D-Wave was okay for that. And so the D-Wave helped solve the mystery there. There's also been a TV show called Continuum. And sometimes you'll see, when you see D-Wave stuff, you'll see the picture in the lower right. Those are actors, not real D-Wave people. We look more, I have a collar on today, so I really dressed up, but we look more like kind of regular people. So we're even making it into the category of fiction. Our hope is to get one of our T-shirts on one of your favorite TV shows in the not-too-distant future. With that, we'd just say, in this whole sort of the continuum of things that we can do and how to prove how these machines work, sort of the question for me is quantum supremacy the right way, or is that, a long ways away in a land far, far away? Or will there be a killer app, the Quantumator, or will it be a bunch of little quantum cubs who are learning how to do things, and eventually they grow up to be bigger cubs? My guess is, so 5 years ago, I would have said there will be a killer, no doubt within 5 years there will be a killer app in quantum computing. Quantum supremacy to me is interesting, but I'm kind of a systems engineer focused on customers and applications and things. I thought we would have had a killer app. We don't yet. But I do see these hints of these little cubs of things that are starting to work, and I think pointing the way. So with that would end, you can have copies of all these slides, plus these websites have the real customer presentations of almost all of this stuff. So Yanni, I don't know if we have time for a question or not, but if we do, glad to try to answer one if the Terminator lets me see out there.
We saw in the last talk a comparison of power for problems, I think. The applications where you see, comparable results for your tests, do you have any feeling for the power consumption?
Yeah, absolutely. Our machine uses, and this was true for the 500 qubit, the 1,000 qubit, and the 2,000 qubit, and we believe it'll be true for the 5,000 qubit. Machine uses between 20 and 25 kilowatts. No matter the size of the problem or how many iterations you run, that's what it uses. And so, so sort of in the world that we've all grown up with, how do you actually use and apply these computers? People say, can you run my application or some part of it? How fast? What does it cost? And then how much power does it consume? So eventually, when we get to be able to run applications and you can demonstrate performance, these quantum computers are going to win on performance per kilowatt. There's no question about that in my mind. So long way to say 20 to 25 kilowatts, kind of no matter the problem. But the challenge so far, of course, is we can't demonstrate great performance, but we're starting to approach that. Great. Well, I can't see anyone else, and I think a break is up next. So again, thank you very much. Appreciate it.
Thank you very much. Thanks. Great talk. Great.